Imagine a massive passenger airplane weighing tens of tons accelerating down a runway. Within seconds, it reaches incredible speed, lifts off the ground, and climbs thousands of meters into the sky. Under its wings are powerful machines that make this possible: jet engines. But how can an engine with no propeller push such a heavy aircraft through the air at speeds close to 900 kilometers per hour? The answer lies in one of the most fundamental principles of physics: Newton's third law of motion. This law states that every action produces an equal and opposite reaction. If a jet engine pushes air or hot gases backward at high speed, an opposite force pushes the aircraft forward. This force is called thrust. A jet engine works by accelerating a large mass of air in one direction. The faster the air is pushed backward, and the more air that moves through the engine, the greater the thrust produced. Although a jet engine might appear simple from the outside, internally it is an extremely sophisticated machine. Modern jet engines contain thousands of precisely engineered components and operate under extreme conditions. Temperatures inside certain parts of the engine can exceed 2,000 degrees Celsius, while internal components rotate at tens of thousands of revolutions per minute. If you like similar educational videos, please like, subscribe, and share the video with your friends. Despite this complexity, the fundamental operating principle of a jet engine follows a clear sequence. First, the engine must take in air from the surrounding atmosphere. At the front of the engine, there is a large fan or intake that pulls air into the engine. In modern airliners, this fan can be several meters in diameter and moves enormous amounts of air every second. Once inside the engine, the air enters the compressor. The compressor consists of many stages of rotating blades. Each stage compresses the air slightly, increasing its pressure and density. After passing through multiple stages, the pressure of the air can become more than 30 times higher than atmospheric pressure. Why is compressing the air so important? Because fuel burns much more efficiently when mixed with high-pressure air. The compressed air then enters the combustion chamber where it mixes with aviation fuel, usually a refined form of kerosene. The fuel-air mixture ignites and burns continuously. Unlike piston engines, where combustion occurs in separate cycles, a jet engine burns fuel in a continuous flow. This produces extremely hot, high-energy gases. These gases then flow through the turbine. The turbine consists of rows of blades that spin as the hot gases pass through them. The turbine is connected by a shaft to the compressor at the front of the engine. This means that some of the energy from the hot gases is used to power the compressor, keeping the entire engine running. But not all the energy is used internally. The remaining gases exit the back of the engine at very high speed. This high-velocity jet of gas creates the thrust that pushes the aircraft forward. However, the engines used on most modern passenger aircraft are not simple turbojet engines. Instead, they use a much more efficient design known as a turbofan engine. Once air enters a jet engine, the next critical step is increasing its pressure. This is the job of the compressor, one of the most important components inside the engine. Compressor is made of multiple rows of rotating and stationary blades arranged in stages. As the rotor blades spin, they accelerate the air and push it toward the next stage. Stationary blades then redirect the airflow so it enters the next rotor stage at the optimal angle. Each stage increases the air pressure slightly. Individually, the increase is small, but after passing through many stages, the air becomes extremely compressed. In modern jet engines, the compressor can increase the pressure of incoming air more than 30 times compared to atmospheric pressure. This compression is essential because high-pressure air allows fuel to burn much more efficiently. The compressed air then moves into the combustion chamber. Inside the combustion chamber, fuel is injected through special nozzles. This fuel is typically aviation kerosene, known for its stability and high energy density. The fuel mixes with the compressed air and ignites. Unlike a piston engine where combustion happens in repeating explosions, a jet engine burns fuel continuously. As long as air and fuel are supplied, combustion remains stable and constant. The burning fuel produces extremely hot gases. Temperatures inside the combustion chamber can exceed 2,000 degrees Celsius. At these temperatures, many metals would normally melt. To withstand such conditions, jet engines use advanced materials called superalloys. These materials often contain nickel, chromium, and other elements that maintain strength even at extremely high temperatures. Additionally, turbine blades are carefully cooled. Many of them are hollow and contain small internal channels through which cooler air flows. This cooling air forms a protective layer around the blade surface and prevents overheating. After combustion, the hot, high-energy gases move into the turbine. The turbine consists of rows of precisely shaped blades that extract energy from the fast-moving gases. As the gases pass through the turbine, they cause the blades to spin. The turbine is connected to the compressor by a shaft running through the center of the engine. This means that the turbine uses some of the energy from the hot gases to power the compressor at the front of the engine. This creates a continuous cycle. The compressor pushes air into the combustion chamber, combustion produces hot gases, and the turbine uses part of that energy to keep the compressor spinning. The remaining energy continues toward the exhaust, where the gases accelerate out of the engine at extremely high speed. This high-speed exhaust creates thrust. However, in modern commercial aviation, most thrust does not actually come from the hot exhaust gases alone. Instead, it comes from a different concept that revolutionized jet engine efficiency: the turbofan. If you look at a modern passenger airplane, the first thing you will probably notice is the enormous fan at the front of each engine. These fans can be over 3 meters in diameter, and their blades are made from extremely strong yet lightweight materials, such as titanium or carbon fiber composites. At first glance, this fan might look similar to a propeller. In reality, it is part of a highly advanced jet engine design known as a turbofan. The turbofan engine is the reason why modern aircraft can fly longer distances, burn less fuel, and produce less noise compared to early jet engines. In older turbojet engines, almost all the air entering the engine passed through the combustion chamber. This air was compressed, mixed with fuel, burned, and then expelled out of the back at extremely high speed. While this produced strong thrust, it was not very efficient. Engineers eventually realized that a much better approach was to accelerate a large amount of air slightly, instead of accelerating a small amount of air extremely fast. This idea led to the development of turbofan engines. In a turbofan engine, the air entering the engine is divided into 2 separate streams. The first stream flows into the core of the engine, where it passes through the compressor, combustion chamber, and turbine, just like in a traditional turbojet. The second, much larger stream of air bypasses the core of the engine and flows around it through a bypass duct. This bypass air is accelerated by the large fan at the front of the engine. Surprisingly, most of the thrust produced by a modern turbofan engine comes from this bypass airflow, rather than from the hot exhaust gases. The ratio between the amount of bypass air and the amount of air flowing through the engine core is called the bypass ratio. Modern commercial jet engines often have bypass ratios of 8:1 or even 10:1. This means that for every kilogram of air flowing through the combustion chamber, 8 to 10 kilograms of air bypass the core and are accelerated by the fan. This design dramatically improves fuel efficiency. It also reduces noise, which is extremely important for airports located near cities. Another interesting feature of modern jet engines is that they often use multiple rotating shafts. Inside the engine, there may be 2 or even 3 separate shafts rotating at different speeds. For example, the large fan rotates relatively slowly, while the high-pressure compressor deep inside the engine rotates much faster. This multi-spool design allows each section of the engine to operate at its most efficient speed. The engineering challenges involved in building these engines are enormous. The fan blades must withstand incredible forces created by rotation. The tips of the blades can approach the speed of sound, and even small imperfections could lead to dangerous vibrations. Because of this, each blade is manufactured with extreme precision and carefully balanced. Despite their complexity, modern jet engines are incredibly reliable machines. They are capable of operating for thousands of hours under extreme temperature, pressure, and rotational forces. But how are these engines controlled during flight? How does the pilot manage such a complex system safely? A modern jet engine must operate reliably in many different conditions. During takeoff, it produces maximum thrust. During cruise flight, it runs in a more fuel-efficient mode, and during landing, its power is reduced significantly. Managing such a complex machine would be extremely difficult without advanced control systems. For this reason, modern jet engines are controlled by sophisticated digital systems. The most important of these systems is called FADEC, which stands for Full Authority Digital Engine Control. FADEC is essentially a computer that manages every aspect of the engine's operation. This system constantly monitors dozens of parameters inside the engine. It measures rotational speeds of different shafts, exhaust gas temperature, air pressure in the compressor, fuel flow, and even vibration levels. Using this data, the FADEC computer adjusts fuel injection and other operating parameters to keep the engine running safely and efficiently. Because of this technology, the pilot does not need to manually control the internal workings of the engine. When the pilot moves the throttle lever, the FADEC system automatically determines the correct amount of fuel and the proper engine settings needed to achieve the desired thrust. Safety is one of the most important priorities in jet engine design. Every component must pass extremely demanding tests before it is approved for use in aviation. For example, fan blades must be able to survive impacts from birds at high speeds. During testing, engineers deliberately fire bird carcasses into running engines to ensure that the blades and engine casing can withstand such events without catastrophic failure. Jet engines are also designed so that if an internal component fails, fragments remain contained within the engine casing. This protective structure prevents debris from damaging the aircraft. Another remarkable feature of modern jet engines is their efficiency. Thanks to high compression ratios, advanced materials, and turbofan technology, modern engines convert a large portion of fuel energy into useful thrust. Despite this impressive efficiency, engineers are constantly working to improve aircraft propulsion. One promising direction is the development of open-rotor engines, which combine characteristics of turbofan engines and propellers. These designs could significantly improve fuel efficiency in the future. Another area of research involves hybrid and electric propulsion systems. While large commercial aircraft still rely on jet engines, smaller aircraft may eventually use hybrid electric power systems to reduce fuel consumption and emissions. Even as new technologies emerge, the core principle of jet propulsion remains the same as it was when the first jet engines were developed. Air is drawn into the engine, compressed, mixed with fuel, burned, and expelled at high speed. The resulting jet of fast-moving gas produces the thrust that pushes the aircraft forward through the sky.